In number theory, Ostrowski's theorem, due to Alexander Ostrowski, states that every non-trivial absolute value on the rational numbers Q is equivalent to either the usual real absolute value or a p-adic absolute value. Definitions. Raising an absolute value to a power less than 1 always results in another absolute value. Two absolute values and on a field K are defined to be equivalent if there exists a real number C greater than 0 such that the trivial absolute value on any field K is defined to be the real absolute value on the rationals Q is the standard absolute value on the rails. Defined to be this is sometimes written with a subscript 1 instead of infinity. For a prime number p, the p-adic absolute value on Q is defined as follows. Any non-zero rational x can be written uniquely as, where a and b are integers not divisible by p and n is an integer, so we define proof. Consider a non-trivial absolute value on the rationals. We consider two cases. It suffices for us to consider the valuation of integers greater than 1. 4. If we find C and R plus for which for all naturals greater than 1, then this relation trivially holds for 0 and 1, and for positive rationals and for negative rationals case I, n greater than 1. Consider the following calculation. Let A, B and n be natural numbers with A, B greater than 1. Expressing Bn in base A yields then we see, by the properties of an absolute value. Therefore, however, we have, which implies, now choose 1 less than Bn such that B greater than 1. Using this in the above ensures that A greater than 1 regardless of the choice of A. Thus, for any choice of A, B greater than 1 above, we get i.e. by symmetry, this inequality is an equality. Since A, B were arbitrary, there is a constant, for which, i.e., for all naturals n greater than 1. As per the above remarks, we easily see that for all rationals, thus demonstrating equivalence to the real absolute value. Case 2. n1 as this valuation is non-trivial, there must be a natural number for which n less than 1. Factorizing this natural yields p must be less than 1 for at least one of the prime factors p equals pj. We claim then in fact that this is so for only one. Suppose per contra that p, q are distinct primes with absolute value less than 1. First, let be such that, by the Euclidean algorithm, there are m, n, z such that this yields a contradiction. So we must have pj equals alpha less than 1 for some j, and pi equals 1 for ij, letting we see that for general positive naturals. As per the above remarks we see that all rationals, implying the absolute value is equivalent to the p-adic 1. One can also show a stronger conclusion, namely that is a non-trivial absolute value if and only if either for some or for some. Another Ostrowski's theorem. Another theorem states that any field, complete with respect to an Archimedean absolute value, is isomorphic to either the real numbers or the complex numbers. This is sometimes also referred to as Ostrowski's theorem.